Before considering examples of subvector spaces, let's see examples of subsets which are not subvector spaces, okay? So examples. Let's consider V to be R squared, R2. Therefore, we have that R2 is in correspondence with a plane with the coordinate system, two-dimensional coordinate system. Okay. Now let's just take a curve inside this plane, this for example, and let's call this W. Now we wonder whether something like this could be a subvector space. Now notice that property number 2 implies that in order for W to be a subvector space, the identity element of V has to belong to W. Okay. This because if we take alpha to be 0, which is a perfectly legitimate scalar, alpha times W will always 0 times W will always give the identity element inside V. Okay, since this has to belong to W, then the identity element of V will be in W, and this is a necessary condition for W to be a subvector space of for W to be a subvector space of V. 0 in V. Therefore, we see that the vector space structure on V does not give a vector space structure on W, okay? Because one of the reasons is because the identity element does not belong to this subset, okay? Okay, so now let's consider the following W. Is exactly the same as the one before, but I translated in order to have the curve passing through the origin. Okay, so now the subset W does have the origin, the identity element inside itself. So we still ask ourselves the question whether W is a subvector space of V. Okay. So let's look now at the second condition. So the second condition in its more general form, not just in this implication, the second condition says that for each vector little w in W, all its multiples have to belong to W. Okay. So let's just take any vector here, let's say here, in W, and let's see whether multiplying it by any scalar, we get that the product still belongs to W. So as we have seen in the previous video, multiplication of a vector by a number results in some element of the line passing through the vector that I'm considering and the origin. Okay. So for example, if I take 2 times this vector here, little w, so if this is little w and I take 2 times, I will be getting a vector somewhere here. So somewhere here there will be 2 times w, which clearly does not belong to my curve. In fact, I can prove, and we will see in later lectures, that all the points of this line are vectors of the form alpha times w for some alpha. Okay. So in particular, 2 times w in this very special case does not belong to w. Therefore, this w, even the translated one through the origin, is not going to be a subvector space. So this shows that w is not a sub V vector space. Okay. However, I can take any set bijection from W to R. Let's call this F. F is in this direction, and use F to give W some vector space structure, which is not going to be a sub-vector space structure of V, but is going to be some vector space structure. Okay, I can of course define this new structure on W in letting V1 plus W1 plus W2 equal W3 if and only if W3 is, well, if and only if f of W1 plus f of W2 equals f of W3. Okay, and likewise I can define lambda times W to be the element f minus 1 of lambda times f of W. Okay, so this is a product in R. I'm using the R vector space structure on here, and here I'm using also the R vector space structure and taking this sum. Therefore, I can use this bijection to move the vector space structure on R over W. This will give a perfectly defined vector space structure on W, but this structure will not give W a sub-vector space structure of V. It will be just a vector space structure defined, so there will be some zero inside here that will be f minus 1 is of the zero of R, which will be a point, and then the sum here will be defined according to the sum in R following these rules. Okay, so W can be given a vector space structure, but no vector space structure can make W a sub-vector space of V, as we have shown here.